Hello and welcome everyone to the fourth lecture in the module on water quality and human health. Just to remind you that all of the lectures are posted on our YouTube channel, and you can subscribe to this channel so you will get notifications when new videos appear. I think we're completely up to date at the moment with the videos, the lectures. So if you've missed anything, please go and watch there. Also for this lecture again, please post your questions in the chat during the lecture. We will collate them, and then during the Q&A session after the lecture, we'll ask questions to Milton and have a discussion. So please just feel free to put your questions in the chat. So today's speaker is Dr. Milton Campbell. He holds a degree in oceanography from Rio de Janeiro State University. He has a master's degree in remote sensing from the National Institute for Space Research and a PhD in biological oceanography from the University of Sao Paulo. And he worked as a postdoctoral research at the Bedford Institute of Oceanography in Canada. He currently works as a senior researcher in the Earth Observation and Geoinformatics Division of the Earth Science Coordination Department at the National Institute for Space Research in Brazil, where he is the leader of the Monitoring Oceans from Space Laboratory and also a permanent professor of the postgraduate program in remote sensing, where he is responsible for different topics, including introduction to remote sensing and remote sensing of climate, and where he also supervises master's and PhD students. Since 2002, Milton has acted in senior roles, including as the head of the Remote Sensing Division and as the Earth Observation Coordinator Deputy, and he has been a member of the Municipal Council for the Environment in São José dos Campos and the Municipal Council for Preservation of the Historical, Artistic, Landscape and Cultural Heritage. He also acted as the director of the Sao Paulo branch of the Brazilian Association of Oceanography. Milton has been awarded with the honor of cartographic merit in the degree of officer by the Brazilian Society of Cartography. And he continues to be an active member of scientific committees for events related to oceanography and remote sensing. He's quite a track record, so he acts as a reviewer and associate editor of scientific journals, and he's a member of several committees, including the Deliberative Council and chairman of the Fiscal Council of Brazilian Association of Oceanography, of the Executive Committee of the International Ocean Color Coordinating Group, of the Municipal Urban Development Council of São José, and of the Advisory Committee of Marine Science, and importantly, of the Decade of the Ocean Science in Brazil under the Ministry of Science, Technology and Innovation in Brazil. Milton develops remote sensing and geotechnological applications in wide-ranging topics in oceanography and environment, including ocean color, the monitoring of marine and aquatic ecosystems, phytoplankton biomass and primary production, surface fields of temperature and wind, mangroves and coral reefs, and offshore wind energy. And more recently, his research has focused on the use of Earth observation data in studies of water-associated diseases, which I assume he is going to talk about today. The floor is yours, Milton.
So thank you very much, Emma, for the introduction, and good morning, good afternoon, good evening, everyone, depending on where you are. So let me share my screen. Can you see my slide, Emma, please?
Yes, perfect.
So again, my name is Milton Campbell. I'm a satellite oceanographer working at INPE, which is the Brazilian National Space Research Institute. I'd like to thank you for the invitation to participate in this Module 8 of this training course on water quality and human health. talking about applied geotechnologies for ocean and human health. I also thank to all the audience here present today. So the health of human populations is constantly influenced by the environment and patterns of space occupation, which is why the use of geotechnologies in the analysis of the spatial distribution of health problems makes it possible to determine risk locations and also delimit areas that concentrate more vulnerable situations. So the basic idea here is to comment on the use of geotechnologies from smartphones to remote sensing, among others, applied to the study of water-associated diseases. And we are going to talk about the types of databases used, ways of georeferencing or geocoding, of obtaining social demographic, environmental, and also remote sensing variables, about the identification of the social epidemiological profile and its relationship with the variables, and mention about some spatial and temporal analysis. So briefly, after this introduction, I will mention about who you are, what we do, and then you talk a lot about geotechnologies and showing some case studies briefly. And at the end, if you have time, I'd like to comment on relevant aspects to ocean health, human health, and Earth observation. So INPE is a civil body of the Ministry of Science, Technology, and Innovation of Brazil, and completing 62 years in this year, in 2023. INPE's priority engagement areas include the United Nations 2030 Agenda for Sustainable Development, the Paris Agreement, and the Sendai Framework for Disaster Risk Reduction. And after its restructuring in 2020, the areas of Earth observation, Earth system science, meteorology, and climate were all integrated in an Earth science general coordination, where I work in the Earth observation and geoinformatics division. At the institutional level, we build a family of Earth observation satellites named the CIBERS 1, 2, 2A, 3, 4, 4A, and more recently Amazonia 1. And we have the capability and infrastructure for satellite tracking and control, not only our own satellites, but also international missions, with a ground segment to receive, process, archive, and distribute satellite imagery and derived products. Also developing geotools for image and data processing and analysis, making a continuing effort in education at the graduate and extension level, also organizing and participating in technical scientific outreach activities and events. Research, development, and innovation activities are carried out in different topics, such as oceanography, inland waters, agriculture, urban and vegetation studies, as well as in the area of geoinformatics, including geographic data mining, digital image processing, and spatial analysis. More applied and technological projects and even services I provided to society, such as monitoring deforestation in Brazilian biomes, monitoring forest fires, weather and climate forecast and studies, Terra Brasilis platform, and more recently, the Brazil Data Cube initiatives. And now our Monitoring Oceans from Space laboratory develops efforts in studies on ocean color, coral reefs, a little bit with inland waters, also studying mangroves, ocean atmosphere and land-ocean interactions, ocean climate variability, offshore wind power, environmental characterizations, and monitoring. And our involvement with the area of spatial epidemiology or health geography was initially given by the invitation of the dear and esteemed Dr. Trevor Platt and Dr. Shubhasa Chandranath to participate in a scoping meeting on the topic of reducing the risk to human health from water-associated diseases held in Abingdon last 2018, and which was organized under the auspices of the Blue Planet Initiative of the Intergovernmental Group on Earth Observations GEO, with seed funding for the meeting from the Partnership of Observation of the Global Oceans POGO, where around the advantages of having a network of committed specialists working on various aspects of the problem were recognized. And later, during a visit to the Plymouth Marine Laboratory, Dr. Trevor came up with the idea of proposing an initiative like the Onward, and taking the opportunity of an announcement of opportunity from the UK Research and Innovation as part of the Global Challenges Research Fund. We submitted a proposal which was approved in 2019. And we had some problem and delay before we could start the project. And without a doubt that our most sensitive issue was the loss of the outstanding, brilliant leadership of Dr. Trevor Platt. And without Shuba's strength and willingness to accept to take the lead as director of the Onward Network, and without the support of Nandini Mendon and all the members of the board, it would be difficult to be here today. So once again, I sincerely thank Shuba and everyone who supports us. So in the field of health, surveillance is related to the care practice and health promotions of citizens and mechanisms adopted for disease prevention. So in addition, it integrates different areas of knowledge and addresses different topics, such as policy and planning, territorialization, epidemiology, health disease process, living conditions and health status of population, environment and health, and work process. So from here, surveillance is basically distributed among epidemiological, environmental, sanitary, and workers' health. And what we can do in the context of health surveillance. So we believe that it is possible to develop efforts that can be useful, for example, to epidemiological surveillance, insofar as it recognizes the main notifiable diseases and investigates epidemics that occur in specific territories. And in addition, it acts in the control of these specific diseases. Environmental surveillance should be dedicated to interference of physical and social environments on health. So actions in this context have privilege, for example, the control of water quality for human consumption and the control of disease transmission vectors, such as insects and even rodents. So our intention, in addition to advancing scientific knowledge, training and qualifying human resources, is also to generate data, information, and products that can be used in strategic actions associated with health, environment, and climate change issues. You must have seen in other previous presentations that water-associated diseases may be or are caused by microorganisms, natural toxins, chemicals, pesticides, and even heavy metals disseminated or transmitted through water. So studies on these diseases need to encompass environmental, socioeconomic, demographic, and climatic aspects, such as, for example, hygienic sanitary conditions, access or lack of access to treated water, socioeconomic status, water recreational activities, climate, floods, and environmental disasters, among others. And main modes of transmissions include the lack of water or adequate sewage network, contact with the skin or mucous membranes, ingestions of contaminated water, and also vector-borne that grow in water. Some of these diseases are notifiable in Brazil. Our colleagues and our group have developed studies on hepatitis A, leptospirosis, schistosomiasis, malaria, dengue fever, among other diseases in Brazil. Today, we are not going to present any of these studies in deeper details, but we will be able to cite some examples of applications throughout that presentation. And of course, we will always be open for future clarifications in cases there are people interested in the studies. So wherever the disease of interest, it's important to know its transmission cycle. So for example, leptospirosis is a worldwide infectious disease with epidemic potential, especially after a heavy rainfall caused by a bacterium called Leptospira. Leptospira interrogans is pathogenic to humans and animals with more than 200 serologic variants or serovars. So humans usually acquire leptospirosis through direct contact with the urine of infected animals or a urine-contaminated environment. Human-to-human transmission occurs only very rarely. So according to the World Health Organization, more than 500,000 cases are reported each year for leptospirosis. It is an important zoonosis given its social and economic impact in terms of hospitalization costs and even lethality. The disease affects animals and humans, commonly leading to acute infection. And in urban areas, it's synanthropic rodents are the main natural reservoir of the disease's bacteria. So familiar animals, such as cats and dogs, may also be important reservoirs. Humankind is considered as an accidental and terminal host within the transmission chain of leptospirosis. The incubation period can vary from 2 up to 30 days, from the infection to the appearance of the first symptoms, and in general, socioeconomic, environmental, and climatic factors must be taken into account, and they change in each environment over the time. Schistosomiasis is an acute and chronic parasitic disease caused by blood flukes, trematode worms of the genus Schistosoma. So estimates from the World Health Organization show that at least 250 million people required preventive treatment in 2021, and schistosomiasis transmissions has been reported from 78 countries. So people become infected when larval forms of the parasite released by freshwater snails, they penetrate the skin during contact with infested water. Transmission occurs when people suffering from schistosomiasis contaminate freshwater sources with feces or urine containing parasite eggs, which hatch in water. And in the body, the larvae develop into adult schistosomes. Adult worms live in the blood vessels where the females releases eggs. Some of the eggs are passed out of the body in the feces or urine to continue the parasite's life cycle. Others become trapped in body tissues, causing immune reactions and progressive damage to organs. Schistosomiasis is prevalent in tropical and subtropical areas, especially in poor communities without access to safe drinking water and adequate sanitation. It is estimated that at least 90% of those requiring treatment for schistosomiasis live in Africa. And there are two major forms of schistosomiasis, intestinal and urogenital, caused by 5 main species of blood flukes: Schistosoma mansoni, japonicum, mekongi, guinensis, and Iamatobium. Schistosomiasis mostly affects poor and rural communities, particularly agricultural and fishing populations. Women doing domestic chores are infested in infested water, such as washing clothes, are also at risk. Migration to urban areas and population movements are introducing the disease to new areas nowadays. With the rise in ecotourism and travel to very remote areas, increasing numbers of tourists are contracting schistosomiasis. And hepatitis I is an inflammation of the liver caused by the hepatitis A virus, HAV. The virus is primarily spread when an uninfected and unvaccinated person ingests food or water that is contaminated with the feces of an infected person. This disease is closely associated with unsafe water or food, inadequate sanitation, and poor personal hygiene. Hepatitis A does not cause chronic liver disease, but it can cause debilitating symptoms and rarely fulminant hepatitis leading to acute liver failure, which is often fatal. World Health Organization estimates that approximately 7,000 persons died from hepatitis A worldwide per year. And hepatitis A occurs sporadically and in epidemics worldwide, with a tendency for cyclic recurrences. Epidemics related to contaminated food or water can erupt explosively. They can also be prolonged, affected communities for months through person-to-person transmission. Hepatitis A virus persists in the environment and can withstand food production processes routinely used to inactivate or control bacterial pathogens. The hepatitis A virulence is age-dependent. More intense effects are observed for elder people, and the disease is mostly asymptomatic for early ages. The hepatitis A virus is transmitted primarily by the fecal-oral route. That is when an infected person ingests food or water that has been contaminated with the feces of an infected person. So the incubation period of hepatitis A is usually between 2 weeks to 1 month. A basic view shown here illustrates the relationships between the agents, such as virus, bacterium, etc., human vectors and hosts living in the same environment. So it is intended to use different methodological tools to help us study the transmission, habitat, and the environment through digital models. And this type of approach in the universe of geoinformation can be represented here in the forms of layers of different topics of interest, such as sanitation, drainage, houses, municipalities, or other geopolitical borders, satellite, and other types of images, among many others. So in this general flow chart that I will be repeating, showing during my presentation, we try to summarize, let's say, 4 major steps or bins of steps that can be employed in studies of water-associated diseases, actually other diseases as well, and based on geotechnologies, including remote sensing data, of course. So these groups would be related to the source of the data or databases, also data processing, data analysis, and spatial analysis. And it should be mentioned that some examples or reference come from Brazil. Sorry for that, but there are similar ones in other countries and regions and even globally. So let's consider that someone intends to carry out a study on some water-associated disease in a certain region. Here, as an example, we show the region of Cametá, which is located in the state of Pará, in the Amazon region of Brazil. So the objective was to collect in situ primary data, also to better learn and know about the reality of the situation and local conditions. So meetings with the community and local authorities should be held, biological or epidemiological sampling sites should be defined, some on-site laboratory analysis may be considered, and questions about the storage and transport of the samples should also be considered in a mission like this. It is very important to consider the collection of the geographic coordinates of the sampling points, and this can be obtained using GPS receivers or even smartphones and tablets that are even smartwatches as well, as you have nowadays. And other supporting information may or should also be used when available, such as regional and municipal maps, satellite images, indications of roads, streets, river limits, and among others. And it is recommended to consider the visualization of the geographic data during the field work itself. And the visualization of the sampling points can be superimposed on cartographic bases, such as maps or satellite images, for example. And common formats are GPS exchange and KML files. So someone might ask, do you need to be connected to the internet for the smartphone's GPS to work? So the answer is no. Even offline, it's possible to open a GPS application and get the exact point, the position on a map. Shown here are examples of exporting or importing GPS coordinates in the Google Earth application and viewing GPS data in TrackMaker software. Both are free. And there are other options available, such as the Android TS GPS, among many others. Here we have on the left an example of a simple application of GPS data in a study on the spatial distribution of Bionfalaria genus in the state of Minas Gerais in Brazil. The genus Bionfalaria comprises gastropod mollusks that live in fresh water. And these are of medical or public health importance because some species are intermediate hosts for Schistosoma mansoni. And on the right, another example of application of the use of smartphone data in a paper on Schistosoma mansoni infection and related knowledge among school children in an endemic area of Minas Gerais prior to educational actions. Tabulated or tabular data from different sources are also very much used. And here we see an example of a source of information available in Brazil at the national level through SINAM, which is the Notifiable Diseases Information System. DataSUS is the IT department of the Unified Health System in Brazil, and among many other things, they keep a web portal available on the internet. So data from health services are collected at the municipal and regional level in forms. These forms can be on paper or directly digitized on computers connected to the internet. So we have a lot of issues with filling these forms indeed. Also, two applications are available from download, the TabNet and the TabWin. The TabNet is an epidemiological, socioeconomic, and demographic database, among other data, and the TabWin is a tool to manipulate, visualize, and even analyze the data. It is also possible to obtain global data from institutions such as the World Health Organization, and here showing an example on schistosomiasis, or from the same source but about malaria. So WHO, they have developed the malaria treat maps interface with maps, dashboards. You can download data and also have a lot of outreach and educational material. And similarly, data are made available by the World Bank. And here you have just an example showing some demographic data from the globe. Talking about tools or geotools, if you wish, EpiInfo is made available from Centers for Disease Control and Prevention in the US, which is it is a public domain suite of interoperable software tools designed for the global community of public health practitioners and researchers. It provides for easy data entry form and database construction, so you can build your field form if you wish, a customized data entry experience and data analysis with epidemiological statistics, maps, and graphs for public health professionals or people which is interested who may lack an information technology background. So EpiInfo is used for outbreak investigations, for developing small to mid-sized disease surveillance systems, as analysis, visualization, and reporting components of larger systems, and in the continuing education in the science of epidemiology and public health analytic methods at schools of public health around the world. You can download it for free and is available for Windows, mobile platforms, and also for web and cloud computing. Now, let's say you have your tabular data on a digital basis and you want to represent, let's say, the real world from thematic data layers like the examples shown on this slide, as digital elevation model, satellite imagery representing different land uses and land covers, water bodies, your epidemiological health or biological data, etc. But you need to have all data georeferenced pixel by pixel. So programming languages like Python and geographic information systems like QGIS are very powerful tools for visualizing, processing, and analyzing different types of geographic data. Thus, it is strongly recommended that those who are not yet familiarized with these powerful tools should make an effort to start using them. Logically, if you already dominate other software like ArcGIS or programming languages like R, these are indicators that you already are on a good path. So apps like Google Earth can be very useful in many ways, such as helping to locate a point of interest on a map or on a satellite image. So it's possible to obtain an address, for example, and with Google Maps, it's also possible to develop several interesting applications. But in this case, you want to indicate the possibility of obtaining geographic coordinates from a location or address. In addition, there are ways to create maps of interest. BetGeo, for example, is a useful application to create a map or a Google Maps alike from your spreadsheets. So maps create a visual representation of a list of addresses or other locations that simply cannot communicate. So we think that the maps can expose so much more information that can be communicated through tabular data. With tools like this, you can map open data. And there are thousands of public Excel documents, HTML tables, and government CSV files with very interesting information. You can also use groups to break down your data and see trends on a map. or exploring sites on your map with clustering approaches. And of course, Excel and other spreadsheet softwares are great for storing and sharing data. And there are so many analyses that can be performed right in your spreadsheets, especially when dealing with geographic data. But with this type of tool, you can find facts about your location data. And an important feature is to convert geographic fields such as addresses, zip codes, and city names that came in the forms from the field and from the health service into geographic coordinates, which can be plotted on a map. So back to our general flowchart, you can indicate some descriptive analysis which may be interesting, as in a social epidemiological profile and on seasonality. So on the right, there is an example of a study on the profile of hepatitis A in the municipality of Belém in the state of Pará in the North Brazil. And here in this other study on social demographic and spatial temporal profiles of hepatitis A in the state of Pará, Brazil, based on reported notified cases, results are shown on the temporal variation of notified cases of the disease, also per gender and education group, and on the distribution of the predominant infections among age groups. Following our general flow chart, several variables of interest are indicated, including environmental, social demographic, land use and land cover, as well as different types of vector or raster matrix data, such as satellite images. So in Brazil, social demographic data can be obtained from the Brazilian Institute of Geography and Statistics, IBGE, and sanitation, hydrological, and water quality data can be obtained from National Water Agency, ANA. And satellite image can be obtained or acquired from many different sources, and I can mention a few of those, such as USGS in US for Landsat Archive, INPE in Brazil, of course, Earth data from NASA. If you go to ESA, Copernicus, you have a bunch of very nice, friendly accessing interfaces for direct download, Copernicus Open Access Hub, and you can also access Copernicus program and from Sentinel satellites data via the cloud during different tools that are available for free. And of course, you can also still get data from EUMETSAT, ISRO in India, JAXA in Japan, among others. Still talking about data sets of interest, WorldClim is a database of high spatial resolution global weather and climate data. This data can be used for mapping and spatial modeling. The data are provided for use in research and related activities, and some specialized skill and knowledge may be needed to use them. However, it's good to announce that the site offers good help material to guide users, and more easily available data for the general public will soon be made available. Users can download gridded weather and climate data for historical, near current, and also future conditions from climate models. Google Earth Engine combines a multi-petabyte catalog of satellite imagery and geospatial datasets with planetary scales analysis capabilities. Scientists, researchers, and developers use Earth Engine to detect changes, map trends, and quantify differences on Earth's surface. Earth Engine remains free for academic and research use. And using the web-based code editor from Earth Engine, it's possible to develop algorithms with instant access to very large databases. So if you haven't registered yet, you can do so by following the link for non-commercial users. Non-profit organizations, academic institutions, educators, news media, indigenous governments, and government researchers are eligible to use Earth Engine free of charge. Continuing with our flowchart, we see here on the right, you see here an example of a study on correlations between environmental and social demographic data and hepatitis A transmission in Pará State, Brazil, where different remote sensing variables were used in the studies, such as daytime and nighttime temperature, vegetation indexes, altimetry, and precipitation, and all those were obtained from the Earth Engine platform. So cloud computing also allowed the deriving other variables, applying relatively simple algorithms for estimating turbidity in the water, total suspended matter, and also some hydrological indexes. And here, it is another study also using the Earth Engine platform on the identification of heat islands in the municipality of Belém, in the north of Brazil, and also obtaining satellite-derived temperatures from satellite data. Next, we will briefly show examples of studies that developed the different spatial and temporal analysis, producing what you call chloroplat maps, risk maps, using interpolation and sometimes ecological models. So the risk of transmission of urban schistosomiasis in northeast region of Brazil was mapped using the map algebra analysis technique by neighborhood, according to the environmental conditions, which is shown here on the right. In a space-time analysis of leptospirosis in 2 municipalities in Lower Tocantins, North Brazil, choroplatic map was used to show that the census tract with higher incidence for leptospirosis were located in urban areas and not in rural areas. And the heat maps of the incidence indicated that the notification cases were mostly spatially aggregated. And these results, they were validated somehow by means of the Moran analysis with a Moran index higher than 0.3 down here. And the LISA analysis indicated that the spatial dependence of incidence was census tract specific. Sorry. In the study shown at the left, the histogram gradient boost regression model was used to predict hepatitis A transmission in the state of Pará, North Brazil. Predictions were highly correlated with notified cases with a relatively low residual error. And based on the results, an hepatitis A risk map was built for the study region. And the obtained risk map can be thought of as an auxiliary tool for public health strategies. And in the study show at right, a space-time scan statistic was applied in order to investigate the most likely clusters and respective temporal windows in a time series of notified cases of hepatitis A virus infection in the same study region. Some of the 6 clusters discovered had time windows and spatial locations concomitant with publicly reported emergency situations associated with severe flooding, for example. The objective of this study shown here was to diagnose risk environments for schistosomiasis in coastal localities of Pernambuco in northeast Brazil, applying the kernel estimator, elevation maps, and distance map in a geographic information system computational environment. Environmental variables, including temperature, salinity, pH, total dissolved solids, and water fecal coliform dosage, were collected from Bionfalaria breeding sites or fossil. And the kernel estimator identified the clusters of positive patients and fossil of Bionfalaria, and the digital elevation map indicated the areas of rainwater concentration. At the same time, the distance map showed the proximity of the snail fossil with schools and health facilities. According to the authors, geoprocessing techniques proved to be a competent tool for locating and scaling the risk areas for schistosomiasis and can subsidize the health service control actions. These studies here, they present examples of the use of interpolators. On the left, the IDW interpolation method was used to determine the spatial distribution of abundance of Bionfalaria snails collected along the coast of Pernambuco, northeastern Brazil. IDW means inverse distance weighting, which is a type of deterministic method for multivariate interpolation with a known scattered set of points. The assigned values to unknown points are calculated with a weighted average of the values available at the known points. And on the right, geostatistics is used to make inferences about the presence of the species of Bionfalaria gravata, Tenagóphylla, and Straminia, which are intermediate hosts of Schistosoma mansoni at the São Francisco River Basin in Minas Gerais state, Brazil. One of these statistical procedures, known as kriging, allows the classification of categorical data in areas where data are not available, using Punton sample sets with points. So kriging is a geostatistical interpolation technique that considers both the distance and the degree of variation between known data points when estimating values in unknown areas. A kriged estimate is a weighted linear combination of the known sample's values around the point to be estimated. The result here is a map of species and risk area definition. More than a single map of the categorical attributes, the procedure also permits the association of uncertainties of the stochastic model, which can be used to qualify the inferences. The occurrence of schistosomiasis is directly linked to the presence of its snail intermediate host Bionfalaria species. Knowledge of geographical distribution, habitats, and behavior of the snails in relation to the climate is essential for guiding measures for disease prevention and control. So this model distribution of Bionfalaria glabrata and Bionfalaria straminia in schistosomiasis non-endemic areas of the metropolitan region of Recife in the state of Pernambuco, northeast Brazil, were based on environmental data and estimates of snail distributions in endemic and neighboring areas. So kriging was used for determining the spatial distribution of these two snail species, and maximum entropy was used for modeling their ecological behavior. Now, the middle Paranapanema region in the state of São Paulo, Brazil, is an area with high diversity for Bionfalaria species, with municipalities historically marked by cases of schistosomiasis transmission. Current distribution and future predicted distribution of habitats of Bionfalaria species, they were evaluated in this watershed region. The study encompassed 55 municipalities in the region, which were analyzed through the maximum entropy algorithm. Environmental data included the world climate, hydrosheds, topodata elevation models, and other malacological data. And for the future period, the Jim2-Yes climate model was used. Due to climate change, Maxent showed a high probability for the maintenance or permanence of Bionfalaria gravata habitats in the identified spots, also an expansion of scattered spots, and approximately 50% probability that the species will spread throughout new suitable areas. The idea in this ongoing or almost finishing study is to propose and apply a conceptual model for potential landscapes related to schistosomiasis production in the same middle Paranapanema watershed shown before. Also, to identify and characterize in these landscapes the levels of potential risk of exposure and contact between humans and the intermediate hosts, the Bionfalaria gravata, Straminia, and Tenagóphylla snails. In the phase 1, a typology was built and the data set was selected and produced. So the typology consists of 10 types of landscapes considering the environment where it's possible to have cases of schistosomiasis, also environments where it is possible the existence of the snails, the intermediate hosts, and other environments where it is not possible to have neither of those. The classification result indicates a high global accuracy, above 95%, which allows us to propose a map of areas of potential occurrence, suitable areas, and unsuitable areas for the study region. So I believe that we have covered, if not all, a large part of this big general flow chart. We could go on showing other examples of application, but perhaps this is not our objective from here. So let me see if I have some time to comment on some aspects that may be relevant to ocean health, including marine ecosystems, marine fauna and flora, human health, and how Earth observation, including remote sensing and geotechnologies in general, can add value, connect, integrate, and support relevant developments in a very broad view. The state of the ocean is increasingly described in terms of ocean health. However, I have seen in the literature and in some workshops and meetings that some colleagues argue now that the health metaphor can somehow be imprecise or ambiguous. So maybe the idea of ocean health misrepresents the Earth's history of ever-changing and adapting ecosystems through time. Indeed, alternative terms are already in use, such as the ocean we want, preconized by United Nations Intergovernmental Oceanographic Commission. So the vision of the United Nations Decade of Ocean Science for Sustainable Development is the science we need for the ocean we want. The Ocean Decade is a convening framework for diverse stakeholders to co-design and co-deliver solution-oriented research needed for a well-functioning ocean in support of the 2030 Agenda. Capacity development, ocean literacy, and the removal of barriers to full gender, generational, and geographic diversity are essential elements of the decade. The global ocean, which is considered here as an interconnected system of Earth's oceanic waters, play a central and positive role in human life, including through the climate system. Damage to the ocean is far-reaching in its effects in terms of productivity, species diversity, and resilience. Global ocean activities are putting population at risk. That are challenges, and they are not few. It's worth mentioning that it's important to understand and better manage the many aspects of oceanic sustainability, ranging from sustainable fisheries to ecosystem health to pollution. Another important challenge relates to the realization that the sustainable management of ocean resources requires collaboration across nation states and across the public, private, civil sectors, and on a scale that has not been achieved yet. A healthy ocean sustainably delivers a range of benefits to people now and in the future. We cannot have healthy people and a healthy planet without a healthy ocean. The pressures are intense, but recovery is possible. The ocean is critical for the global climate system and planetary health. It has absorbed 25% of all carbon dioxide emissions and captured 90% of the additional heat generated from greenhouse gas emissions, but is now warming and acidifying. So concern over the deterioration of the oceans has generated the demand for systems able to access ocean health globally and on observing systems delivering the data to support this assessment, which are now being developed. In parallel with public health systems, a system to assess ocean health should evaluate the occurrence and severity of a set of syndromes of concern through a series of indicators composed from a parsimonious set of ecosystem essential ocean variables delivered by a coherent and robust observing system. GOOS is focused on three key application areas: operational services, climate, and ocean health. It consists of a multitude of individual surface and space-based observing systems owned and operated by a plethora of national and international agencies with different funding lines, alliances, overall priorities, and management process. GEO is an intergovernmental partnership working to improve the availability, access, and use of open Earth observations to impact policy and decision-making in a wide range of sectors. In addition to over 70 work program activities and initiatives such as Blue Planet, MBON, GeoHealth, AquaWatch, that addresses global needs, coordination, and knowledge gaps. The Geo community is building the Global Earth Observation System of Systems and has already made more than 400 million data and other information resources available via its GeoPortal. POGO seeks to expand international support for ocean observing through innovation of the ocean observing system, capacity development, and outreach advocacy. In support of GEO and as a spatial component of GEOS, CEOS developed the virtual constellation concept. A virtual constellation is a coordinated set of space and ground infrastructure from different partners that focus on the observation of a given parameter or set of parameters of their system, as for example, atmospheric composition, land surface imaging, ocean color radiometry, ocean surface topography, ocean surface vector wind, precipitation, and sea surface temperature. Now, the Copernicus program is the European Union's Earth observation program, looking at our planet and its environment for the ultimate benefit of all European and global citizens. The Copernicus Marine Services provides free, open, regular, and systematic reference information on the physical, sea ice, and biogeochemical ocean state, variability, and dynamics across the global ocean and European regional seas. There is a wide suite of Earth observation products that can provide direct and indirect information considered useful for ocean health and public health communities, including climate and weather parameters, as for example, rain, temperature, wind, air quality, humidity, air pressure, also heat island effects on urban areas, storms, floods, and droughts, detection of algae blooms that are harmful to health, water quality, ocean color, sea surface height, temperature, salinity, land cover and land use, loss of biodiversity, among others. Next, you see a few examples of applications. So Aziz Anasi and collaborators showed that phytoplankton emerged as the preferred host of environmental Vibrio cholera in a tropical lake and estuary in Kerala, India. And they proposed to use the quantitative relationship between phytoplankton and the risk of environmental cholera bacteria in the water, using chlorophyll concentration as the measure of phytoplankton biomass. Here in the left, the relationship between satellite chlorophyll and probability of finding environmental Vibrio cholera in brackish and freshwater regions in Vembanad Lake. And in the right is a representative satellite image of chlorophyll for 23rd February 2019. And on D here is the corresponding risk map of environmental Vibrio cholera incidence in the lake, generated from the relationship shown in the previous charts for the two parts of the lake. So on the right, Mahifani, Hakor, and collaborators presented a review on the potential use of remote sensing data for Vibrio cholera studies, indicated that remote sensing chlorophyll was correlated with cholera cases, habitat suitability, and density in oysters. And covariates investigated in addition to chlorophyll A included remotely sensed observations of sea surface temperature, sea surface height, precipitation, and field measurements of salinity, pH, bottom temperature, phyto and zooplankton biomass, river discharge, climate indices, and socioeconomic status. So anyone interested in this subject can also visit the Vibrio Prediction Hub. And as already mentioned, the Open Network for Water-Related Diseases, ONWARD, is dedicated to developing a network of scientists and stakeholders sharing a common interest in better understanding of environmental controls on outbreaks of water-related diseases. The role of societal engagement in countering it and in forecasting, early warning, and risk mapping of water-associated diseases through the use of remote sensing, field observations, and mathematical modeling. More information can be found at this link, as well as if you're interested in joining for free. So please do that. GeoHealth is a Geo Earth Observation for Health project with the objective to characterize the environmental suitability and potential for spread of selected endemic and episodic vector-borne diseases in the Americas. This project develops prototype geospatial models on visceral leishmaniasis and Aedes aegypti-borne arboviruses, dengue, Zika, chikungunya, which have the potential for episodic spread from Latin America and the Caribbean and establishment in North America. Since 2011, unprecedented massive episodic strandings of floating holopelagic sargassum, which is a genus of a large brown floating algae, have been observed along the shorelines of the Gulf of Mexico, the Caribbean Sea, and the tropical Atlantic. Large influxes of floating sargassos in near-shore coastal areas and beaches can cause tremendous harm to marine life and coastal ecosystems, negatively impacting public health and disrupt coastal activities from tourism to fisheries, costing local communities some money. Despite these negative and harmful impacts, harvested sargassum may also provide raw materials for commercial use and presents opportunities for economic development, including agriculture, bioenergy, bioplastics, constructions, and cosmetic, among others. So detecting, modeling, and forecasting of floating sargassum are essential for designing effective integrated risk management, mitigation, and adaptation strategies. So thanks to the US and European Copernicus Earth observation programs, there has been significant progress in global remote detection of floating sargassum. Satellite detection relies on specific algorithms which capture wavelengths of reflected light associated with the presence of sargassum in the signal received by the onboard sensor. Today, satellite data provide ocean color products and other data products that allow detection, quantification, and tracking of sargassum mats over large regions. At the same time, these observations contribute to better understanding of transport, growth, and decay properties of the mats, and provide long-time series to investigate trends and variability patterns. There are also applications of satellite ocean observation data on different topics, such as coral reefs, water quality, mangroves, among others. One of the major impacts of climate and anthropogenic change is on the water quality in regional oceans and inland waters. Degrading water quality induces significant stress on marine habitats, such as coral reefs and seagrass meadows, forcing flow-on effects on fish population reduction, invasive species economic loss to the human populations that depend on the marine resources for employment and recreation. So the ocean holds many of the solutions that humanity and the planet needs, such as improving global food security, reducing climate and weather risks, providing clean energy, and increasing economic growth through blue economy sectors. Understanding the complex cause and effect connections between ocean processes and sustainable development solutions requires new approaches offered by recent advances in high-performance computing, artificial intelligence, machine learning, and digital ocean analysis and prediction systems. Co-designing these tools to deliver the target information needed for policymakers and to achieve the sustainable development goals requires a dialogue between prediction system developers, SDG experts, and the ocean governance sector. And it is only through synchronous layers of capacity development, from entry-level approaches for the wider public to knowledge sharing between experts and high-level decision makers and government officials, that the diffusion of ocean knowledge will turn into ocean action, really. And as blue carbon holds great potential as an ocean-based solution to climate change, while also generating a broad array of co-benefits, it requires good governance and cross-cutting partnerships to ensure credible long-term project results that engage with best practice principles for a blue carbon market that could be sustainable and equitable. The ocean is an important source of climate solution. It is also critical to global economic development and the achievement of almost all the sustainable development goals. So where we are now? The summary and examples presented here is incomplete. Other efforts that deal with pollution, eutrophication, acidification, pharmaceuticals, and other beneficial products, for example, were not presented but deserve consideration. Besides disasters and extreme events, as Shub already mentioned, the technologies exist for making a big step forward the ocean and human health. The ocean decade sets the stage for making rapid progress, but infrastructure and capabilities at institutional level for developing analysis and applications at appropriate time and space scales lag behind. Resources for meeting the requirements on an operational basis are lacking. The scientific and societal justifications are many and irrefutable. Coordinating bodies do exist, and that is all for today. Thank you for your attention.
Thank you, Milton, for this really interesting talk. We have some questions in the chat, so I'm just going to ask those in order of your presentation, more or less. First, I'd like to say you have lots of compliments coming in as well, and thumbs up and applause. So well done.
Before you start, Gemma,
yes.
Could I just make a quick comment?
Of course.
We are at the midway point, I think, of our 16 episodes of training online. And I have been able to attend every one of those so far. And what occurred to me is how much I am learning from my colleagues and friends. So there is a wealth of information in each of these talks. And I find that I'm learning new things at each of these courses. So I want to thank Milton, and I want to thank all those who are teaching in this course. And then I just wanted to say that. I thank you very much, and I give it back to you, Gemma.
Thank you, Shiva. That's a wonderful comment. And I hope that all of the trainees, people online, feel the same, but I have the sense they are learning as well. So just some logistical questions first. So there was a question on whether references for each webinar could be made available before the lectures. I think it's references in terms of relevant literature. So at the moment, we don't provide any information before the lectures except for the lecture name and title. It is a lot of work to organize these lectures, and I can admit that my lecture was finished maybe the day before. So I think this would be too much to ask from us, but I do note that all the webinars are online. You, of course, have the opportunity to ask questions. There are no stupid questions, so if there are things you don't understand, please feel free to ask them in the chat. And then references in the lectures, you can always look them up afterwards. So I hope that helps with learning as well. And then there was a question on whether we could share the Onward website. I saw that someone has posted this in the chat, and also Nandini shared a link to register to the Onward network. So please scroll through the chat messages and you will find those links there. So I think those were all the logistical things. So we carry on with the questions for Milton. And so one of the trainees asked, well, they commented, there's a lot of geotechnological information available to prepare risk maps, but they were curious about how to deal with the uncertainties in that data, and is that something that is considered in the models?
So thank you, Gemma, and thank Isabel for the questions. Yes, you're right, very much. Of course, each data that you are going to use on your modeling approach has its own uncertainty. So when performing this whatever statistical modeling activity, you should also consider some metrics to this evaluation. Okay. So, but the thing is that although even though we do have, we know a priori that you do have these uncertainties, if you do have validation data to check how good or bad is your model, I think you can deal with that. So I think summarizing, you're right, there are uncertainties in the data. We'll have to deal with that through statistical metrics approaches, and there is a need for validating your models. So I think I briefly answered
Thank you.
this.
Yeah, thank you, Milton. So there is another question. You showed a lot of like different sources of data. And I was wondering, how do you decide which data to use in the models?
Okay, so thank you for also raising these questions. I mean, data is an issue because researchers are always complaining that there are gaps of data. Indeed, spatial and representativeness of the data is not well balanced global wide. So, of course, and we're talking about different types of data here. For climate ones, so social, demographic, epidemiological, and many other types, as I mentioned during the presentation. And sometimes you don't have another source. For example, when talking about health data, disease data, epidemiological data, they came from the health service. Sorry, epidemiological data you can go to the field and collect. And we've been observing that I briefly mentioned during my presentation that you do have many issues when the operators, they fill in the forms and they are so overloaded with work and they have so much to do that sometimes very long forms to fill in for very useful information for research, they just don't have the time to properly filling in. And so it's very important to go to them, to talk to them. That's what I was trying also to indicate when I mentioned about doing field work, to learn and to understand the reality where this in situ data was generated indeed. And then you see, and in some places in developing countries, you see that sometimes you don't have a zip code for the address. It is just a geographical reference from the relief, or you have a river and a border of something, and then you need to transmit the idea of the need of geocoding all the information that has been acquired. So, and then you try to do some quality control. And when moving from different scales approach, from continental to regional and to local, and indeed, more and more I am learning that the real thing, that the most strong contribution you can do is at the local scale, but then you need very detailed information and it's very difficult to get with a good quality. And you cannot go to the field and everything. But when talking about more regional to continental or even global scale databases, most of the ones I have cited, they had been validated by different efforts and studies and research, and they are very much reliable. I do, as a professor at the graduate course in remote sensing, I always say to the students that you should not go to the on-the-shelf products without at least checking if available products, they were somehow validated for your region. Otherwise, to be more criterious, you should try to do an effort of validating some of the data locally or regionally. And of course, not all of us are remote sensing or climate specialists to validate or even create new products, but it's an effort of validation or at least learning if data are validated regionally. I think I should recommend this way. So there's not an answer how we choose, and so we are always trying to validate regionally wherever data sets are made available. We also try to go to the field and collect primary in situ data and make those available for the community, and then also trying new data sets that are made available with time as much as possible.
Thank you, Milton. That's excellent advice. Shuba, do you want to add something? I think you're still muted.
Sorry about that. If I could add something to what Milton's detailed reply. If you take the question another way, I read the question to mean, how do you decide which variables to use in your analysis? So I don't know if Milton, you want to answer from that perspective or not. How do we choose the variables that we use in our analysis?
Okay, so let's try to focus on water-associated diseases. Yeah, I'm not a medical doctor. I'm not a specialist in health. So I need to go to the literature and learn and talk with people, specialists from the fields. For example, if you go to a doctor, maybe he don't have in his mind that precipitation is could be an important variable for studying leptospirosis. But us as a scientist, and of course it's in the literature, we know that heavy rain, you can have floods, and water is you can have the transmission of the disease through the water. So we go to the literature, we talk with the people, and also try to have insights ourselves. And also, I think that part of our job, or my job, is also making the link. For example, we know that Copernicus program with Stefano Schuba and collaborators are developing new products. And somehow I have information about it. So, and I am developing a study on schistosomiasis in a watershed here in São Paulo, Brazil. And so I see how I can integrate this, let's say, if not new, but recent variable into the study. And, but one of, maybe was the last example of study I have shown was more or less about this. Because I mean, I have seen in the literature that people go and they see what other studies they have been using or what is documented in the literature as being relevant. But there are so many other variables of interest that maybe sometimes you still don't have gridded or satellite derived, because satellite derived products, they are very accessible for a wider community. So that's why people are more and more using, because those data are gridded and friendly, available, and so on. But you have many other variables that you still cannot derive from satellite directly, but you can try to make empirical other types of modeling approaches to derive those other ones. But I was mentioning our last study, and I mentioned about the typology. And this is very new for me. So, because in this case, instead of considering whatever set of variables, we've been, let's say, thinking, I mean, and discussing what would be the landscape, as we're taking this term from the ecology, but so we are not anymore working with you use the variables that they will, through a modeling approach, to derive what you call a topology. It could be understood as a class, you know. And so you have a list of classes of landscapes that you think that then from the typology and not from the variables itself, you can better classify the surface of a region and to find areas of interest, of risk maps, of areas of occurrence or areas of contact, and areas with non-suitable for transmission of a certain disease. So, I mean, this is a line of research indeed, and there is no one only answer for this. And of course, with the power that you have nowadays in hands, with Python and R tools and cloud computing platforms, that of course, and different, and a lot of shared codes for statistical analysis, very powerful ones, and also for testing uncertainties and so on with simulations and etc. And not demanding that much big computing capacity. I mean, so a lot can be done, I mean, with normal desktops and so on. And I think that that's what people are doing. So collecting a huge data set with different variables and from different types, environmental, climate, social, economic, demographic, and so on, and let the statistics, or if you want, machine learning approaches to decide which variables should be kept in the model. I am not this type of guy very much. I'm not also a ocean modeler at all. Shuba knows, Gemma, Tom, Osvaldo, but Lika, but Nandini as well. But this is very much going on nowadays. I mean, many of us are already doing this, so we are taking the opportunity of having the availability of huge data sets and the tools for applying statistical approaches or machine learning, if you wish, artificial intelligence, for defining which are the most relevant or important variables for certain studies. So unfortunately, that is going on nowadays, and I think for the near future, that would be the way. I know I didn't answer, but I think I comment somehow.
Thank you, Milton. You actually touched upon some of the questions that I had in mind of asking you. So there were some questions around whether we can observe waterborne diseases using remote sensing. So you've touched upon this in your lecture, as well as me and Shuba. So we can't directly see them, but we can use environmental and other data to detect them based on empirical relationships or other relationships. Shuba, you want to comment?
Thank you. I wanted to see if we could take the question to a very practical level and see how one might respond when there is a real problem of infectious diseases. And I'm wondering whether Stefano could reply to this question. I see that you are still with us. And I'm thinking about the floods in Italy. I understand that there is now a risk of infectious diseases. So in this kind of a crisis, for example, how could one respond, is my question. Stefano, would you mind taking that on?
Thank you, Shuba. We do have, in fact, a couple of mechanisms in place. The first one is the Charter of Space and Major Disasters, where all space agencies are providing satellite data to a crisis area related to the specific area of interest that is defined by the country that is in the difficult situation. Another service that we offer, still free of charge, is the emergency service of Copernicus, where all the Copernicus data in this case, so this is specific to the Copernicus constellation, so only the Sentinel satellites are provided to the specific area of interest. And in addition, of course, we have a number of pilot projects that we can run specifically to develop algorithms. I mean, even the Vision project that we have with you is a good example, where we take an area that is particularly susceptible to flooding, like Lake Vemabad in India, and then we try to develop products so that for the next time that in case there is another flooding, let's say, we can then apply the specific products for that area. So we try to cover a little bit the end-to-end scenario from, let's say, prediction towards operations during the emergency, and then the next phase will be the development of the digital twins through the Destination Earth program of the European Commission, where ESA is supporting. As you know, there is also the ECMWF, the European Center for Medium and Range Weather Forecast. In that case, we try to have also in place some kind of simulation tools that can help in creating what-if scenarios for specific areas or regions of the world. But this is, of course, coming in the next, I would say, 5+ years to be fully operational. I hope I gave some inputs. I don't think I fully answered all the possible implications of the question, but at least I gave probably some hints.
Oh, you certainly did. Thank you very much, Stefano.
Thank you, Stefano. That actually also touches upon questions about prediction and forecasting of disease using remote sensing. There's a more technical question for Milton. The question is, what were the criteria for choosing the IDW technique in your example that you've provided? And could another technique be used? And the person who asked this question mentions the RBF. I'm hoping that you know what that means, because I don't know.
Yeah, okay. No, thank you, Emma, and thank you, Androniki, for the question. No, you are very much right. I mean, the thing is that it's only a matter of culture, local culture, you know. Indeed, and I don't know why, maybe I guess, but what I wanted to tell you is that, for example, kriging has been, I mean, the main interpolator being used here around. And then there are other techniques to it. And IDW was just a technique that a colleague was familiar with. But, and so just to show that you don't need to only rely on kriging, but of course you can try other ones. It's a matter of trying to derive information where you don't have from points, and then also evaluating, as people already asked, and evaluating the uncertainties that you can have. But that's it.
Thank you, Milton. There's quite a fun question, I think, whether there's an app available for warning about water-related diseases. And so are we able to check water quality for good swimming if we're on holiday? And maybe a more general question is, for some of the examples that you have shown, is this used operationally, like in information provided by government or to NGOs? And so maybe you can comment in that way.
Okay, that's a very tough question. Because first of all, I mean, I take the opportunity that Stefano mentioned about one of the programs. And so we can make a kind of analogy with INPE. In INPE, we also do design some satellites. We try to build those. We don't launch because we don't have a rocket, but we rent that. But we do fly, operate. We have the ground segment where we receive the satellite data, generate the imagery, make those available through the community, and also to promote applications of using this type of data, not only from our missions, but of course from other international and very interesting missions. And there is a lot of research and technology behind that. And providing operational services is a very Shakespearean thing. It's to be or not to be. And INPE has taken the charge of doing the deforestation monitoring of the Brazilian Amazon for more than 30 years in a row. And nowadays we are doing not only for the Amazon forest, but also for other Brazilian biomes. So Brazilian Cerrado Savannah, and the Caatinga, and the Pampas, and the Pantanal, so the Brazilian biomes. In parallel to that, we also provide the service of real-time monitoring of fires. So this is a 24/7 activity, and is very, very much demanding. And I should confess that myself has been enrolled with the health sector for not so many years. A few other colleagues, they have been working in this field for more years. And many years ago, we have approached, let's say, the health sector epidemiological and health surveillance sectors of some states, secretaries, and also at national level, mentioning to them about all these geotechnological tools that can be made available and useful for them. And indeed, after a decade of joint efforts, they have built their own expertise. And so there are some institutes at the national or at the state level that now they are experts in this type of analysis. Many of the co-authors in those of these examples, they came from the sector, so they don't need us anymore. They become experts. Of course, we still work together, and they're very open-minded because my colleagues, they came first and they teach them, and they are the ones doing the front end of this type of services that you have raised, and not us. And so you have the COVID-19, and then you have emergency calls all the time. If it's not dengue fever, it's chikungunya, and can be even a few outbreaks of yellow fever here and there, malaria, and just mentioning some water-associated diseases. And so this is a very tough work. And unfortunately, my institute, we don't have the mission, neither the funding, neither the staff for providing the service, but we do collaborate with these guys in the front end, on the front line, supporting them somehow. And very recently, I don't know if you're aware, in Brazil, we have a very serious issue with indigenous people, Yanomami. And after the federal administration change, there was a task force for putting a database set together, for orienting the best approaches. And that was like, say, damage control indeed. But so at the end of the day, we are not in charge of doing this, but to try to collaborate with them as much as possible. And those guys are my heroes because they are saving lives and they are saving expenditure of millions in mitigating efforts. But it is not our mission. And there are many other, branches and applications that you must take care of in terms of pollution, in terms of disasters, flooding that you mentioned before. So there is so much to do, and unfortunately, we have only a small percent of ISA and other colleagues, and so, but we do what is possible. Sorry for that.
Thank you, Milton. I think we all share your thoughts that we do what's possible and we would wish we could do more. There's a question about connecting to national and international networks. So you've shown a lot of examples of data sources and open processing tools so that users and our trainees can access and analyze data. But how do the users of that data and of those tools effectively bring their results to the attention of some of the large organizations that you've mentioned and the wider scientific community? And with the idea that normally we go through publications, but these for some people can be quite expensive, and findings and the insights sort of get lost in the bulk of research that is going on. So do you have any advice on how to connect to decision makers, to large organizations?
Well, that's another tough question. I agree 100% with all of this. Now, first of all, I do agree that somehow having our papers published could be costly, and it is very arguable. And nowadays there is a lot of argumentation about this. But at the same time, we do have, let's say, journals where you can have your work, your studies published for free. So you should try to focus on those. And some of those are very highly ranked, but if not all, but many of those. And the second, I think, strong point here is about communication. So besides publishing scientific papers, and people are discussing that a lot, that a big effort must be done in improving communication skills and ways with other stakeholders and non-governmental agencies, government agencies, and different types of institutions. And there are people really dedicated in doing that. Unfortunately, we cannot do everything, and some people have more or less skills for this or that and so on. But and I think that if we all do our part, whatever it is, collecting data, making information available for others, doing analysis, or focusing on communication, education at different levels. I think at the end, and there are some coordination agencies, as Shuba mentioned, and I repeated here, in place. Because it's a huge work also to coordinate. So Stefan was mentioning about one program, but imagine they also do all the chain of action activities I mentioned for INPE, they also do, and also need to coordinate everything. So it's not an easy task, but the effort must be done and is being done. And so you don't need to lose your, you can sleep well, thinking that if you are doing your part. And of course, being part of networks, participating in different forums such as this one, and online activities, which save a lot of time and money with traveling. But although traveling is, and personal contact is a very rich experience, and so I think we will be there. But it is, I agree that if you are not coming for, let's say, for a center of excellence or a highly recognized institution and want to knock the door of a government or something like a big institution, is not an easy task. But as my former general director also teach me, if you want to go fast, you go alone. But if you want to go far, let's go together.
That is a really wonderful comment. Thank you. I have a question about the second part of your lecture, which was related to ocean health. And so this is about ocean health and the protection of the oceans. And the question is, how do you foresee the introduction and reinforcement of marine protected areas for this topic? How important are MPAs?
Yeah, thank you for this question. Wasn't in the radar for this, but I agree, it's very much important. And if not all of us, but some of us are aware that United Nations is advocating, and the countries have signed to increase the percentage of marine protected areas global-wide. But this is very tricky, but this should not be taken as an administrative task. What I mean, for example, let's say I have access to the fishing sites of a certain region in the coast of São Paulo nearby. So I know where the fishermen they go. So let me take the areas where they don't go, where there is no oil and gas exploration, where there is no tourism activity, where there is no recreational activity, where there is not much use of it. And then administratively, I will propose the creation of a marine protected area because there is no conflict of interest. So we should avoid this type of approach. I think that marine protected area should be based on an ecosystem management approach, and then defined ecological, let's say in a broader view, oceanographic, biological, whatever climatic reasons for creating these marine protected areas here and there. So the marine spatial mapping is not only for administrative purposes such as management of conflict of interest, but for the real, let's say, in my opinion, reason for having those areas created. And you have very good examples worldwide and also in Brazil, where you can see easily, in not so long period of time, the positive consequences of having these marine protected areas when they are reasonably, no need to be well-defined areas, just reasonably defined very well. And these decisions should be made based on scientific and technical information and avoid the political ones. That would be my comments on this.
Thank you, Milton. There are a couple of questions left. So there was a question related to how to monitor sargassum using remote sensing, and Shuba has put some information in the chat about this. There's quite a lot of research about this, and so she's given a reference to a paper on this. And then there's a question about models, ecological models. So the question is whether you could explain more about the max-end ecological model. Where do you find the input to the model? And were you able to compare the data with existing or other environmental factors using the model?
Okay, so thank you. So if you go to the literature, you can have different approaches of modeling, and the ecological one is one that's really, let's say, is very appealing to me, although not that much effort has been put on this. But and then I have shown these two case studies, and the maximum entropy approach, as far as I know, and I'm not a big expert on this, but I have seen very much being used on how to say population dynamics, you know, from different species and group of let's say animals, for fishes, sharks, just mentioning about the sea. So there are tools available, but in this case here today, what you have shown is using this type of tool for water-associated disease studies. But it doesn't mean that this is the best or the only one approach you can have. There are other approaches, and nowadays is more or less relatively easy to get the tools, I mean the codes, because people are sharing codes using GitHub like platforms and so on, and Python with R, and then you can try different ones. And what will vary when choosing from model to another would be, of course, your skill or familiarity with one or the other, and the amount of input data that which one will be required. And I also suggest to see exactly which one will provide you with uncertainties, evaluations of your results. And I think that would be your best choice. So the easiest and the lighter and of a way of validating your work.
Thank you,
But of course,
Milton.
you can discuss more later if you wish.
Thank you, Milton. I think that was the last question, unless I've missed something, TJ. I think we've run through the questions. So thank you very much, Milton, for your lecture, and also for answering all of those questions. And thank you everyone for being here. That is the end of this session, and hopefully we will see you next week when we start with a new module, a new topic. So thank you everyone.